Problem number 2685. Count the number of complete components. You are given an integer n. There is an undirected graph with n vertices, numbered from 0 to n minus 1. You are given a 2D integer array edges, where edges I equals AI BI denotes that there exists an undirected edge connecting vertices AI and BI. Return a number of complete connected components of the graph. A connected component is a subgraph of a graph where there exists a path between any two vertices, and no vertex of the subgraph shares an edge with a vertex outside of the subgraph. A connected component is said to be complete if there exists an edge between every pair of its vertices. Return the number of complete connected components of the graph. A connected component is a subgraph of a graph where there exists a path between any two vertices, and no vertex of the subgraph shares an edge with a vertex outside of the subgraph. Okay, so it's basically like a group. Okay. A connected component said to be complete. Complete means there exists an edge between every pair of its vertices. Okay, so any combination of its vertices has an edge. So like so this will be complete. This is a complete. This is complete. Okay, there exists a path between any two vertices. Don't think this is. So return the complete components. Oh, it's 3. So 0 to 1, 0 to 2, 1 to 2. It's complete. This is complete. Like every combination, and this is not, so it's only 1. Yeah. Okay, so yeah, so okay, first of all we need to check the range. Okay, so the questions that I want to ask is the range of n and I think A and B will be in the range of 0 and n minus 1, but will there exist okay, the length of h at the range, and then like is AI equal to BI, and does there like multiple edges in between AI and VI. Yeah. Okay, so no, and it's only it will be unequal, and the length of edges will be okay. So we will have at least one node. And at most 50 nodes. The length of edges will be oh. Yeah, I'm thinking like, yeah, this is kind of interesting. Like the edge length will be at most, and yeah, it's basically the total number of nodes. Yeah, like if you have one node, then you don't need edges. If you have two nodes, it's one. If you have three, it will be three edges. If four nodes, then 2, 3. Oh, it's the combination. Like have three nodes. And then you take two, so it's combination of 3 and 2. Oh, 2 and 2 will be 1. 3 and 2 will be 3. 4, 2 will be 6. So, okay, so a complete a complete connected component with m nodes will have a combination m with 2 nodes, edges. That will have the edges count will be okay, but now we need to return the number of complete connected components. Okay, so given the edges, how can we know the number of? Yeah, we can know the group. yeah, we may know there are 3 groups, but can we know the edges number in each group? Yeah, like for 0, we have 2. Yeah, so the problem will become, how can we check if this component is complete? And the thing we know is that if this component is complete and it has n nodes, the edge count will be the combination m with 2. But how? The problem. How can we find the edges count of this component? Can we know? If we use DFS, we start from 0, and then we have its connected component. We have its connected nodes 2 and 1. So maybe we will plus 1 when we find one connected node, because the edge will plus 1. And then when we are at 1 will be connected to 0 and 2. And okay, so if not visited, we will add 1. So we will be, now we'll have 2. And when we got to 1, since 1 is connected to 2, we will traverse to 2, and 2 will not be added, because though 2 will be connected to 0 and 1, we will not visit them because it has all been visited. So the current path will be 2, current edges count will be 2, and then back to 0. Yeah, I think then we will only have 2. We will not count this. Or 0, 1 not visited, and 1, 2 is visited but 0 is or let me think. If we have 4 nodes, well, there Yeah, because we will not have multiple edges between the same two nodes. So if yeah, I'm thinking of like if we count every edges before checking it's visited or not, then we will have double. Yeah, we will count the duplicates. Yeah, I'm thinking if this is possible. Yeah, if we have 4 nodes, then yeah. I think if it is like counted double times, yeah, if the edge count is doubled, then it is a complete connected component. Because we will, yeah, there is no multiple edges between AI and BI. So, okay. The time complexity of this. So I will have I will first have a DFS. I will use depth first search, and then I will use it to find the connected components. Start with node I and find the connected component, and then calculate the edges count in the at the same time. And then if edges count, since we will count, like for these 3 nodes, I will count 0. I will count before checking if it is visited, if the node is visited. So every edge will be counted twice. So if edges multiplied by calculate edges count, calculated count equals to combination node count. Oh, we also need to count nodes. Edge count, node count. Node count will be after visited, checking visited. Combination will be node count and 2, then multiply by 2. Then it is complete. Yeah. Okay, so time complexity will be think of n nodes, and for each node, its edges, it will be edges count will, yeah, the total edges count will be e, so n plus e. Okay, let's start. So first of all, we will have the visited set, and let's have our DFS first. Oh, and we will for loop every node. So okay, for I in range n, if I not in visited, then we will start DFSI. Oh, and we should know if it is complete or not. Okay, if complete, then answer +1. We will first create the adjacency list. So adjacency list. So nodes equals default dict, and default will be a list, empty list for edges in edge. I'll have A and B. And since it is an undirected edge, so node A will append B, and we also need to append, and we'll have B append A. And okay, so that's our adjacency list, and let's move on to our DFS. So we will have node count equals 0. We will have edges count equals 0, and we'll have the complete count equals 0. Yeah, and at the end we will return the complete count. Okay, so for after this DFS, we will get its node count. Okay. Yeah, so if edges count equals combination node count 2, then it is complete. Then complete count plus 1. So DFS it's now then visited, so we will have visited at I. And for the connected nodes, for node and nodes I, we will first add is edges count plus 1. If node not in visited, node count plus 1, and we can have it like, we will add it here, and we will traverse the connected node. Yeah, kind of like this. So okay, I will first try a single node, like and will be 1, and edge will be empty. Yeah, so for this case, no adjacency list. Okay, so for n is 1, I is 0, 0 not in visited, DFS 0, visited at 1, at 0, so it's now 1, node count plus 1. For node and node I, empty. Then, okay, so we will return. So DFSI is finished. Edges count is 0. It equals to combination node count 1 with 2. Oh, let's see. I'll check the Python combination. Oh, it should give you, you should give a iterable. Okay, then if I only want to count the count, then calculating only the total count, you will have comp 5 choose 3. Okay, so we'll have comp, and for 1 choose 2, I think it will be 0. So edges count 0 equals to 0. Okay, yeah, it's 1, so it's correct. And maybe edges case. Okay, maybe we have 4 and we have edges 0, 1, and okay, and 2, 3. Then it is a complete, it has to complete count. Or maybe, okay, maybe like this. 0, 1. Then we have 3 complete counts. Then, okay, so adjacency this will be will be 0, 1. So that's start of DFS, and is 4. We'll start from 0. 0 not in visited, so we'll have DFS 0. It will be visited at 0. And node count will +1. Okay. For node in nodes I 0. It's at node 1, and edges count will be added by 1. Then if node not in visited, 1 is not in visited, so we will have DFS 1, and it will be added to the visited set. Node count will be added again, and for 1, it's an empty array, so we will not execute this for loop. We will return, and then since 0 only has 1 node connected, we will also return this for loop, and it's the end of the DFS. Okay, so we'll finish and we'll do here. So edges count is 1, combination count, node count 2 will be 1. So 1 multiplied by 2 is 2. Oh, sorry. And it's not correct. Oh, sorry. I will have 1 with 0 as well, since we will append these 2. So when we visited 1, it has node 0, and edges count will be added to 2. So if node not in 0 is already in the visited set, so we will not execute this bottom 9s. So edges count is 2, combination is 1 multiplied by 2, so it's equal. Complete count will be +1. So we'll have 1 complete component now, and then it's node we have I equals 0, then we will have I equals 1, but 1 is already in the visited set, so we will skip it. We will turn into node 2. Then node 2 is not in the visited set. We have DFS 2. So now we will add it to the visited set. Node count. Oh, we should reset the node count. And edges count and complete. So I think we will reset here. Node count is 0, and edges count is 0. Oh, maybe reset only if we have used. So that's here. Okay, so we will reset this. it's 0, 0, and okay, so now it's number 2. We have added to the set. Node count will plus 1. For node and nodes I, it's an empty array. Yeah, so we will not execute this, and we will finish our DFS if edges count is 0. Combination count will be 1 with 2. 1 choose 2, so it's 0, and 0 multiplied by 2 is 0. So complete count will be added by 1. It's now 2. Yeah, the same thing will be as the node number 3. Yeah, so complete count will be 3. Yeah, I think edge case are covered. Okay, that's brown. Oh. So it's non-local, node count. Do we need? I think edges count also need. Yeah. Okay.